Good morning, good evening, good afternoon, depending on where you are joining us in the world. Welcome back to the MEng Alliance seminar series. This is our first seminar of the semester. And it's a great pleasure to have you joining us today, and a great pleasure for me to introduce our panel of discussers today. So again, I'm Brian Anthony. I'm the faculty lead for the MEng Alliance. I also have another hat that I wear in the conversation today, but I'll really be your host today. Today's seminar is on manufacturing, from theory and education to research and practice. And with us, we have Professor Dave Hardt, who is the faculty lead for the Master of Engineering in Advanced Manufacturing and Design program. We have Jose Pacheco, who is the industry co-director for the same degree program, and Arjun Chandar, who is a graduate of the program, but also the CEO, CTO, and founder, co-founder of Industrial ML. And I'll be a faculty advisor for one of the projects you'll hear about today. So you'll hear about the principles of manufacturing, how they're taught, and how they're put into practice. Please raise your hands via the virtual chat function, and we'll try to let the presenters get through their talk, but this is going to be more of a panel discussion as we go. And with that, everybody, welcome. And Dave, I'll turn it over to you to amplify your introduction and to kick us off. And I think you also need to share your screen. And Dave, just know you are currently still on mute. There we go.
Okay, well, welcome everyone. It's a pleasure to get a chance to talk to you from the comfort of my office at MIT. Of course, I'm not actually in this office. I'm sitting at home. We thought it would be a better background if you could see that. I want to talk about something that's evolved from our Master of Engineering program. It's not something that we sort of sat down and thought up in a back room, but something that evolved by observation and by hard work through our program, and we'll call it the principles of manufacturing. And it really starts with a simple question that we ask ourselves and ask students: what is manufacturing? And of course, you'll get as many answers as there are people in the room, but certainly around MIT and certainly in the Department of Mechanical Engineering, it will revolve around things like, well, it's making things, it's the process of machining, it's photolithography, casting, forging, the processes that actually make things. But then, you know, over time, and particularly those of us who've been involved with sort of factories and the business of manufacturing, we say, well, no, it's also things like supply chains and logistics, Internet of Things. Now we're into machine learning and cobots, if you know what those are. I just learned the other year. And all these other things. And the question is, are those things manufacturing? And we kind of came to the point of view that no, these are pieces of a larger thing. And that larger thing is really a process, a system of making products, combining what was on the prior page, which for lack of a better term, I'll call technologies, to meet commercial demands. In other words, you have to survive being able to do this. Of getting to the marketplace with what you need at the rate that you need and in a timely fashion. So actually meeting a customer demand. Obviously, cost is extremely important. Quality goes without saying, is that if you don't have that, then the other two don't really count. And flexibility, that is the ability to change as the market requirements or the design requirements or the technology requirements ask you to do that. So having said that, we asked the question then, what is unique to manufacturing? Well, one of the things, and we stress this with a lot of the classes, is its continual flow of new material. If you're just making one thing, or you're not making anything, there's no material involved. But if you're making, continually making things, products to send out to the marketplace, you're always flowing through what I'll call new material. So there's this concept of flow, continuous progress through time, through an operation. And you flow this through unit processes. We talked about those a little bit just before, but a series of unit processes that perform a number of different transformations. And even for the simplest product, there is at least a system of these unit processes that has to work together. No factory is an island. So in fact, there's very few, if any, products that are made where everything is made under one roof. The River Rouge may be the one exception to that with Ford back in the Model T days, but nowadays you're buying and selling to multiple suppliers and from multiple suppliers. And then we get into this idea, and so you can see the idea of things flowing through the factory, flowing through the system, flowing through a supply chain. And then the idea comes up that as I'm making multiple products, you'd like them all to be the same. You don't want customer A to get something different from customer B. You don't want things to not function. And even within your own operations, you don't want components to not work together. So minimizing variation is extremely important. And then another part that comes in is that all of this is done at great expense. It takes a lot of money to make a lot of money, if you will. So we have to put a lot of capital at risk, buying plant and equipment, purchasing materials, and of course, putting people to work to get all this stuff done. That takes a significant amount of capital. And all of this is there to meet a customer demand. So you have this objective out in the future, which is actually also potentially highly variable. And then finally, it has to be done at a commercially viable cost. So it seems like a long laundry list, but we were able to boil that down to these following principles. Flow and variation in processes, factories or process systems, supply chains, and the organization, management, and finances of an operation. So flow, continuous flow of things over time, and the whole idea of variability during that flow. And driven by some very important criteria that you could see from what I just said, driven by measures of quality, the rate at which you can provide these products, the cost at which you provide them, and your ability to not just provide the same thing all the time, but in fact, respond. So what do I mean by the process level? Well, this is just a simple video from a micro-embossing process, but what it emphasizes is you got material coming in and going out and coming in and going out. Every time that robot loads a new piece of plastic into that embosser, there's an opportunity for it to be a variation. The equipment could vary. The machine might not be controlled well. It can certainly wear. What we found, this was actually a process we developed in my lab, what we found is that the material was highly variable. So there's an inherent randomness to these processes, and there's also a deterministic one, things you can control, things you can't. We can describe this analytically, we can describe it operationally, and actually call that a principle at the process level. At the factory level, you're talking about flow of material within a factory. You have tremendous problems here with equipment reliability, supply reliability, various production rates within the factory. So we probably all heard of the problem of bottlenecks. The idea, this is really, I think, focuses on the idea of flow even more than anything else, but where unexpected changes can throw off that flow tremendously. And then at the supply chain level, you're now talking about flows among a lot of different parts of the system, from factory to factory. You've got transportation by air, by ship, by truck, all of these different things combining together, flowing together to supply finally a product at the end. And here's where you really kind of feel this uncertainty in the demand, uncertainty in the supply. You're supplying raw materials in here, and of course that's factory itself could be variable. And uncertainty in logistics here. Now it's not a matter of carrying things from one operation to the other. It's a matter of all of these things flowing together and having so many different moving parts with variability associated with those. And then at the business level, you basically have the idea of putting in capital, energy, and knowledge and getting out product. And so you're flowing in things by buying things, selling things, buying raw materials, as well as the energy and other resources it takes to make things. You also have here at the business level this idea of flow of knowledge. It's quite interesting, and there was a term once coined by a colleague of mine called the knowledge supply chain. And you'll notice here, by the way, a very subtle thing in my diagram, the MIT on the left-hand side is smaller than the MIT on the right-hand side, means you actually gained knowledge in going through this business. And clearly you have tremendous variations you have to deal with here with market conditions, cost of capital, and the capability of the people in your organization over time. So those are the basic principles, and we have codified those into 4 basic classes that all our Master of Engineering students take. We also have an MITx or edX MicroMasters credential called the Principles of Manufacturing, which does these 4 levels of Principles of Manufacturing online, and that's been a fairly popular class. We have a number of graduates of that already. But I kind of want to do just finish up here with a little bit of so what, or how does this fit into things that maybe are a little bit more on the tips of people's tongues. And this has to do with this idea of how these principles fit together with Industry 4.0. I'm going to assume you know what Industry 4.0 is, but let's just say it's the 4th Industrial Revolution. It's where we really bring to bear all of the advanced, particularly information technology that's now ubiquitous. So I think it's useful to say that, as we get to 4.0, we started with the idea of 1.0, which I'll just call it is when we got to standardized parts, and somewhere in the 19th century. And the evolution is then standardized parts. What was the industrial activity that occurred when we were in Industry 1.0? Well, it was flow of materials through variable processes and systems. If you don't believe me, there's a wonderful history of the Springfield Armory that'll make it very clear to you that that's what they were dealing with. And then, of course, mass production in the early 20th century. I have a wonderful video that I can show you of a 1930s Chevrolet factory. And what you see going through there is flow of materials through variable processes and systems. The era that we're, I guess you might say, in and exiting right now, automation, where we have computers doing a lot of the control of our machines and not requiring as much human intervention. So an automated factory, what are the activities going on there? Well, you're right, it's flow of materials through variable processes and systems. So now we add on to this the idea of cyber systems, often used as a shorthand for what we have with Industry 4.0. Yes, you're right, it's exactly the same. So the constant through all of this is, regardless of the technology you're applying to do these industrial activities, to actually accomplish the task of creating these products, you're flowing materials through variable processes and systems. So we have technology and we have the principles. So just to summarize then, the value we think of naming it and teaching it this way is and this is feedback we've gotten strongly from our students, is even those who've been practitioners in industry have said, now I finally have a basis for what I'm doing. Analytical methods that we can use to model this flow, to characterize it, and to control it, maybe in a statistical sense, maybe in a more active sense, and to do it all at all different levels of the enterprise, as I've talked about. And finally, why should we bother to learn them? There's so many things we need to learn. Why shouldn't I just go take a course on 4.0, something like that? Well, my colleague Stan Gershwin, who's I know is here, makes a good point that, we don't want to make ad hoc solutions. We don't want them to be based on politics or opinion or how we've always done it, but really have it based on data, and analysis. And these principles give you the fundamentals for doing that. It is really the world-class standard. It allows you to make your decisions much more quickly, consistently, and more accurately. Personally, I believe it's fundamental to actually achieving the principles or achieving the goals of Industry 4.0 or 2.0 or 3.0. No matter where you are, it can be used regardless of where you are on that evolution. It is really, when you look at machine learning applications, which you'll hear from Arjun about a little bit later, he actually wrote an essay, wrote a significant essay on the Industry 4.0 and the principles of manufacturing. So I'll let him speak to that. And with that, I will turn it back to our host, and thank you all for your time.
Dave, thank you very much. So what I would like to do is, just for maybe 3 or 4 minutes, I'm going to share with you a single video. Let me share my screen and share screen. Here we go. Oops. That is the wrong slide deck. There we go. Okay, so hopefully this video is playing for you, and I'll let it play a couple times in case it's not coming through clearly over Zoom. But Jose asked me to share a little bit, just a little vignette about my research. As you'll see rapidly, I was the faculty advisor for a project that you're going to hear about, or one of the projects that you're going to hear about, and just sharing a little bit of my manufacturing data science research. This is a video, a high-speed video, recorded at about 1,000 frames per second of a diaper packaging line. And what we're seeing now is this printer, effectively, it jammed. But some of the research that I do is, how do I take this high-speed video stream and verify that the thing, not just the appearance of the thing, but the time varying appearance, the trajectory of the thing, is of the quality that we want. And hopefully it came through. There was a little bobble there on the flow of the diaper packaging line. And what we'd like to do is process the video to say, hey, something happened, adjust the machine, either stop it or put a feedback controller around it. So some of my research, the graduate students that I supervise, some of them do work in the analytics, the algorithms. Some people do work in applying these on different applications. And so I just wanted to give that a little bit of a framing to give them some research context to a very applied project. I think with that, Jose, I think I turn it now over to you.
All right, thank you, Brian. And so indeed, let me take over from here, because what Brian showed and Dave talked about were the principles, the underlying concept, theoretical underpinning of what the project that Arjun's going to talk about is all about. And then connecting these principles to specific technology. In part, it's a lot of what we think makes the learning experience valuable for the students, and also an experience that's valuable for the companies that we work with. And so I want to spend just 2-3 minutes talking about this program and how it comes together for us. And so hopefully you can see my screen here, and just very brief background on the program itself. Dave already spoke about the Principles of Manufacturing MicroMasters, which is an online course, but it was born out of bringing out the first semester of this master's program that we have at MIT, which is a 12-month professional degree in mechanical engineering. And it really was designed for practitioners to take the concepts and apply them. And our typical student body has between 2 and 5 years of experience, and they're working on applying these principles of manufacturing, which we believe are foundational and independent of an industry or a product, and using them to, plus with the addition of some technologies that you'll see, applying them to a real world example, a real world project. And just to give you a sense of what the curriculum looks like, you can see here that we divide the curriculum over 2 semesters into 4 parts around manufacturing physics, manufacturing systems, design and development of products, and then of course the business fundamentals. Those items in blue are what we call the principles of manufacturing and are part of our principles of manufacturing micromasters. And the rest are courses that the students are required to take over the year they're here. And the connection between the micromasters and the MEng degree is relatively simple, is that admissions for the MEng degree are open to everyone, of course, but those students, and we had 2 this year that applied from the micromasters, that finished the micromasters, join the rest of the students that are part of the MEng degree, and they receive the first semester of credit as part of recognition of the micromasters. And so they're able to have the foundation that we think is necessary to apply to the projects, and they're able to complete the projects a little faster. And to now give you background about what you're about to hear from Arjun, these projects are thesis projects by the students. And typically, the students work in groups of 3, and I put an asterisk there because sometimes, depending on the size of the cohort and the company, we have 2 or 4 students. And they typically work with the company on site from mid-May to the middle of August. And usually they start working with or meeting with the company starting in the early part of the spring semester around February or March. And these projects are supervised, obviously, within the company by company supervisor, but there's also an MIT faculty member that serves as an advisor to the students and also to the project in general. And the 3 areas that the advisors focus on are the 3 that are the focus of the MEng, which is design, production, or supply chain. And so our faculty members have experience and typically do research in one of these areas, sometimes in multiple. And then, of course, the companies underwrite the cost, and I'll talk a little bit more about that. A successful company project obviously identifies a problem or opportunity that is significant or important to the company and has a quantifiable return on investment. It's not an internship. These are real projects that, again, are applying the concepts to something that is important to the company. And there's usually, for successful company projects, a dedicated contact or team that the students and the advisor can interact with. And that's important because it does take a lot of information, a lot of time in order to really come up to speed and have a successful project. And again, just emphasizing that it's in the fields of design, production, or supply chain. And so some quick considerations about these company projects, because we're always asked about this. And these are the 3 main points that we're always asked about, and I just thought to share them right away, which is that the thesis is publicly published. It's part of our academic work, and so all the work is indeed open to the public, usually 3 to 6 months after the project is finished. But recognizing that the companies underwrite the cost, any patentable material, while of course the students are the authors, is assigned to the company, and the company has the opportunity to then submit a patent for that. And we scrub the thesis for any proprietary IP. Trade secrets, for example, are eliminated. We do sign NDAs, and ideally the companies that we're working with are in the US. More ideal, they are within 1 hour drive of MIT because we do want to work with the company in person. Of course, given the current situation, things are a little bit different. And we've had projects in other states, including California. And so that's the ideal. Of course, this year, because of COVID, I want to thank the companies that we have worked with and who have been extremely flexible with us in adapting to this current pandemic. And so 2 of the projects were entirely virtual. And so to Waters, to Danfoss, to MyTime, and of course to Industrial ML, we'll hear from in a second. Thank you for your flexibility, but you can also see how we then adapt to the needs of the company. And so the last thing I want to focus on is some examples of the project objectives. And I thought I'd go back actually a few years to give you an example of two project objectives from 2011 that I thought really reflected what the projects were about. And you can read here that one project was identifying the root causes of a particular manufacturing process for a company that makes circuit components. And as you read those project objectives, then focus on the expected benefits. And this is important. They're quantifiable, they're important to that company, and it is something that reflects, again, the focus on manufacturing, on flow, on flow and the flow of material, information, and money. And similarly, in the second project, it's now developing documentation, but also providing feedback for the manufacturing processes to identify bottlenecks. Now we're looking at the whole system. And again, if you look at the expected benefits, increasing profitability through improved yield and throughput. We actually quantified that. I didn't put that here. And perhaps something that's less quantifiable, but extremely important to the company and most companies, is increasing the customer service level through accurate production schedule. And so usually when we do this kind of project, that's where we start. What are the project objectives and why is it important? What are the benefits of this project? And so with that, if you have any more questions about these projects, please feel free to write us. And I'd like to turn it over now to Arjun, who, as mentioned, is one of our graduates and co-founder of Industrial ML.
Thank you, Jose. And let me share my screen. Hopefully this.
Perfect.
Great. Are you seeing the version with notes or without notes? Just
with notes. You need to flip it around,
okay.
Arjun.
All right. Sorry. There we go. Does that work?
Perfect.
Okay. Awesome. Hi, everyone. So as Jose mentioned, I'm Arjun Chander. I'm the CTO of Industrial ML. I founded the company a little under 2 years ago now. For about the first year, I attempted to do it while doing my PhD, which eventually I realized was not conducive to a healthy experience on either front. But through that, I got to spend some extended time with Brian, and I'm glad that we were able to establish some really good relationships that led to a really successful set of MEng projects. As Jose also mentioned, I graduated from the MEng in 2014, and I've supervised projects for three different cohorts now. Two of them from my last startup, and then this one from Industrial ML. And I can speak very, very highly about the quality of the students that come through the program and the quality of the program itself, and would highly recommend that that if you are a company that happens to be on this call, that you give the MEng program a look when it comes to looking at internships for the summer. I know Jose doesn't like to consider the students interns. They're more people working on graduate projects. But if you know how to roughly point them in the direction of the right problems to work on, they tend to be very independent to give you a good direction of how to solve problems you didn't even think about in your manufacturing process. And potentially they can generate a lot of IP for you, which they have done for us as well. So I'll give you a few slides of context about Industrial ML itself. Our underlying thesis is that we are solving the problem that legacy factories in particular have of losing money whenever their lines stop. And this can happen for a wide variety of reasons, whether it's quality issues, whether it's worker error, or whether they're machine failures that happen. The image that we're showing here is actually from our first customer. their Daiwa steel tube in Japan. And they are what you imagine when you think of a legacy factory. They've operated their steel tube lines roughly the same way for 40 years. And they have a ton of issues with lines failing about once every hour, and a lack of data being recorded as to why those lines fail. What they need in order to keep their lines running for longer is faster insights as to when failures occur. So if you look at a typical factory's current state, you have a situation where a problem occurs on the line, but you could go anywhere from 10 minutes to 2 hours, and in some cases to days before the problem that occurred gets spotted. Then there is a big effort to do root cause analysis and figure out why the problem happened, which gets complicated by the fact that the problem occurred so long ago. Eventually you identify the cause and you fix the problem. What ideally you would like to do using Industry 4.0 techniques is essentially get to that point of identifying the cause right up front when the problem occurs, flagging that problem, then going through a much shorter exercise to fix it, and regaining a ton of productivity. That's essentially the central thesis of what we're trying to solve with industrial ML. So what are some of the steps that are necessary to regain productivity? Obviously, real-time insights, as opposed to 6-month-old insights, are critical. Integrating quality verification data, such as visual analysis, into your process is critical. Again, I'll use the example of a first customer. They inspect tubes maybe once every hour, which at best gets to 2% of the tubes that they produce. But if you're able to do visual inspection using a camera, you can change that to 100% inspection. And finally, and we noticed this about a lot of the other tools that we looked at in the market, tools are designed for data scientists. And I'm not going to name drop competitors in this forum, but what's very typical when you look at an industrial IoT platform is that there is a suite of algorithms that you can use for machine learning on your data, which are designed to be agnostic to the data that comes in, which also means that they are not very robust to new data. But most importantly, they're designed for somebody with a master's degree in data science to fiddle around with algorithms, come up with some conclusions, and then try to impart that to the other stakeholders in the factory. What an ideal solution should do is provide those insights directly to stakeholders such as line operators, manufacturing engineers, or plant managers, and improve that particular mode of communication so that people can act on the information right away. So that's what our solution is aiming to do. And we are an early stage startup, so we haven't built all of this out yet. But what we aspire to be is a platform that takes in vision data as well as data from existing sensors on a production floor, from PLCs or from enterprise IT sources, and flag defects as they occur, and then using machine learning, correlate the defects that we capture with visual analysis to some of the other quantitative data that we're capturing. And then we package that into actionable information for operators and engineers. So an example of what that might look like is on a dashboard, rather than displaying a million charts that people don't know how to interpret, we have a live stream of a particular point on a production line. And this actually is an example of what a steel tube line might look like. Providing, say, one critical metric for a particular point on the line. And in the event that we're able to identify the trends in that metric, we can use machine learning to provide predictions as to what the metric is going to look like over the next half hour or hour. But most importantly, if we either predict an incident or we identify an incident, we want to provide up front and center that information for an operator as to what the incident was and what are the steps they need to take, which is much easier for them to act on than just a series of charts all on the line. So let me tie that into the projects that we worked on with the MEng team. As I mentioned, we're an early stage startup, and a lot of what I just described, we don't actually have displaying in real time yet. We need to be able to do some of the data analysis offline and then productize it into our real-time system. And as of March, the time frame when we started these projects, we didn't have any of that infrastructure in place because our team was so small, and I was really the only one with the expertise to do any of that work. But through the MEng projects, we were able to accelerate our progress on all of those fronts significantly. We worked on projects in 3 areas. Sarah Wilson worked on developing process control principles that could be applicable to real-time data. And Gautier Lemon and Kylie Yu worked on machine vision projects, one of which was focused on doing high speed and high accuracy detection of defects, and the other of which was based on object detection, which means identifying the location of defects within an image. So I probably should have provided a little bit of context on this earlier, but unfortunately we can't provide live images of the factory for confidentiality reasons. But just as an overview, the customer that we are working with, whose data the students used, has a 15-step process where they take a coiled steel plate, run through a number of continuous operations without inventory between those steps, essentially on a conveyor. And then at the very end of their line, they cut a galvanized steel tube, essentially a tube with a zinc coating around both the inner and outer layers. The line is moving really quickly. It can go anywhere from 1 to 2 meters per second, which means that it's not actually possible to do visual inspection in line unless you have a high-speed camera. So talking a little bit about Sarah's project, her analysis work involved taking 6 months of data that we had captured through our platform and plotting every input that we captured to figure out process control trends. She focused on line speed in particular as the metric to guide decisions for monitoring the line. But she also looked at air pressure, she looked at the furnace temperature, and eventually came to the conclusion that the line speed was the clearest indicator of when changes occurred on the line. Well, I'll give you 2 examples of some of the conclusions she came up with. One was that she was able to show errors in the very assumptions that we were using to do some of our analysis. For instance, when we wanted to put real-time analysis into our platform, we asked the customer to give us their specifications. So for line speed, this is in decimeters per minute. What Daiwa wanted was something between 600 and 1,000 decimeters per minute. And if you exceeded those targets, then we should flag an alert in real time. Well, when we attempted to do that, we were generating alerts constantly because they were outside of those specifications. So we took a look at what Daiwa's actual production looked like. And on the product that they make the most, 43% of the time, it turned out that their line speed exceeded those targets for 100% of the time. But there's a high degree of consistency in that line speed itself. So the information we were able to go back to our customer with was, hey, your specifications are off. You should probably switch to these specifications instead, which makes a significant impact on how you're doing your planning and on how you're categorizing what is good or bad on your line. And the second conclusion that she came up with, which I think was a far more interesting one, was that she looked at a number of periods of raw data, and Dave didn't necessarily hint at this in his overview, but one of the underlying principles of process control is that if you were to just plot your raw data, you should be able to identify some trends visually. But when the raw data was plotted, and this is the top part of this graph, you notice a lot of areas where your line speed is very, very consistent, and then it drops, and then it's consistent, and then it spikes. And if you were to try to come up with process control metrics around something like this, your bands would be very, very wide, and you wouldn't be able to generate alerts for anything. But Sarah looked at this data and found that, okay, this is clearly a case where the operator is lowering the line speed. Maybe we should look at this differently. Let's take a look at a variation chart instead. And when she looked at the S chart, there are high periods of consistency, but there are just 2 periods where the variance of the data spikes. And if we set our alert policies based upon variance rather than based upon raw data, well, now here in this case, we'd only generate 2 alerts rather than potentially 0 or 99% of the time. So part of what we are filing for IP for is that Sarah generated a set of rules around how to look at S charts as a way of doing process control and setting control limits. I can't share that information just yet, but that's something that we can apply to almost any customer, because almost any customer that we look at in continuous manufacturing is going to have cases where they have high periods of consistency with small periods of variation whenever an alertable event occurs. I know I'm running a little short on time, so I'll run really quickly through some of the visual methodology projects. So LPA's project focused on 2 types of algorithms for doing image classification. He was able to get reasonable accuracy with both support vector machines and convolutional neural networks, which are pretty common ways of doing image classification. And he used transfer learning from an open source data set. He actually used 2 different steel image data sets from industry competitions to do his training, and then tested on images collected from our customer in order to validate the accuracy of those. He was able to come up with 2 different algorithms that exceeded 97% accuracy. And in both of those cases, he took those weights and then applied them to new images to do inference, and was able to get image processing to a point where he could process more than 10 frames per second, which is extremely valuable to us because we're trying to do real-time image classification. The second thing that he looked at was to try to expand the number of defective products that we could use for training. And I can speak about this in a little bit more depth when we do Q&A, but he used a couple different methods of data augmentation to create synthetic images, because essentially he had an issue where 95% of the training images he looked at were good and only 5% were bad. So to reduce that class imbalance for training, he created a series of synthetic images which were able to fool a separate algorithm he created to discriminate between real and synthetic. And therefore was able to generate enough images to do accurate classification, which again is useful to us because it means that we don't have to collect 6 months worth of defects at a customer. We just need maybe a handful of defects in order to generate enough data to train. As an example, you probably can't tell which of these is real and which is synthetic. The left one is real and the right one is synthetic. But this is essentially a close-up of a steel tube. Finally, I'll speak a little bit about Kylie's project. She tested 3 different object detection algorithms, and you can see some examples of how object detection works. If a steel tube happens to be running by your line, and it happens to have a defect, the object detection algorithm creates a bounding box around the defect and then identifies what class of defect it is. So she tested 3 different algorithms on this and was able to get to a best case set of results where she had 95% accuracy in classification and 89% recall. By accuracy, I mean avoiding false positives, and by recall, I mean avoiding having actual errors slip through the cracks. So again, extremely useful to us, because if we're trying to allow customers to do data analysis after the fact, knowing where their errors are occurring and how often certain errors occur is extremely valuable to them. So that's everything that I had on my side. I'm happy to answer any number of questions about the project work that was done and some of the ways in which it benefited our customer. But I want to turn it over to Brian, I think.
Yeah. So Arjun, Jose, Dave, thank you. So I send you the virtual and the physical clap here. Participants, thank you for your attendance today. We have some time for questions. So please, you can type in the Q&A or you can raise your hands. And let's see, I thought I saw a hand raised there for a moment. Let me ask a probing question here to Arjun. You know, how do you sort of balance the academic sort of desire for the students need to publish with the fact that you are also sort of sort of filing IP?
Well, in our case, I mean, we kind of got around it by just delaying the publication of the thesis by 90 days. And that being done, we'll have filed for provisionals well in advance of any information that gets publicly disclosed in the thesis. With our customer, it's a little bit more, a little bit dicier, where we just have to review the thesis to make sure that their personal information or any details of their process aren't revealed. But we also made that pretty clear to the students well in advance. So they were pretty good about just providing a high-level overview of what the company was without talking about too many details of the process.
So Bill had texted me or chatted me a question directly. I think it's more to Dave and to Jose. Maybe it's mainly to Dave. The question is, how is Industry 4.0 or sort of data analytics different than what we've been doing in SPC? What's new there? I think that was directed to Dave. But yeah, anybody can take it. Yeah.
I'll give it a shot, and then I'm going to bounce it over to Arjun. But
yeah,
I think basically it's an expansion. SPC, and certainly the classical SPC, evolved in an era when measurement was difficult, expensive, and slow. And one of the big things that's happened with 3.0 and 4.0 is that we've made it cheaper, faster, and in some ways better. So what Arjun was talking about with industrial ML was really an implementation of such a system. So that's my first point. One thing, though, that is still true, and where SPC, as opposed to continuous feedback control, still I think is extremely important, is the fact, and this is a lesson I learned because I went from being a feedback control guy to evolving into more of a statistical control guy, was realizing that no matter what we do, when you ultimately want to evaluate the quality of your product, whether it's an individual component or the whole thing, it's very hard to ever measure that in real time. And so you will always be dealing with sparse data. And so in some ways, the difference between SPC and the more modern machine language is the volume of data you have to work with. If you have a large volume of data, there's a lot of things you can do. If you don't, you can't really use machine learning if you've got 10 data points. But you can do a lot of useful things using SPC. So that's my short answer. If you have another 3 hours, I'll give you the long answer. Arjun, you have any comments?
Yeah. So I think I pretty much concur with what you said. There's nothing particularly new about Industry 4.0 as it relates to the principles of manufacturing. And the long paper that I wrote last year about this essentially came to that conclusion. But it does make it easier to gather larger amounts of data to apply the principles of manufacturing. And kind of the point that Dave was making, there wasn't really a standard for visual analysis in process control. Certainly not ubiquitous across manufacturing 20 years ago. Whereas now you can use high-speed cameras to capture tens of thousands of images in just a few minutes. Similarly, there isn't necessarily a standard to capture 20 hertz worth of data, from a sensor, whereas in the 1980s you might be looking at gathering like one data point every minute or one data point every 15 minutes because somebody had to manually record it. So having enough data to do good process control has become easier. Now, on the flip side of that, there is some danger if you were trying to do feedback control on data that you're gathering as it's happening. I think the example of using variants to set alerts that Sarah used in our project is a good reason why that's potentially faulty. Because if we just use raw data to say you're outside of this range, you need to make this change, that would have led to alerts being flagged literally every second. Whereas taking a step back, looking at your data through the right lens, that still requires a level of intuition about application of the principles that Industry 4.0 is not going to just provide for you.
Thank you. And Jose, I want to give you the last 30-second question, and I'm gonna while you're doing that, I'm gonna ask Teresa to bring up the exit slide so people know what's happening next week. So how do companies get involved? What's the process if I have this interesting project that I would like as a candidate for doing this? What's the timeline? How do I start to do that?
Right. So the first thing is just reach out to me, Pacheco at MIT. Simple Google also, you'll find me. And usually we start having the companies present to the students in November so that we then are able to work together to figure out, again, what the expectations are, what the project scope is going to be. And then later in the spring, we're able to start working together. And I think the general concept here is that these projects are meant to both provide something that is tangible as a benefit to the companies, to the students, but also serve as a way of exploring how we apply these concepts, not only the principles, but like your research, Brian, and see how they can be applied in a real world example to give us feedback so that, again, feeds the next set of projects. And so the companies are benefiting from the previous projects that have come before as well.
Very good, thank you. Arjun, Dave, Jose, thank you very much. Participants, thank you for your time and attention and your questions. And we have additional questions, so please feel free to reach out. I just wanted to sort of close with saying, welcome back to the seminar series. Every week, Wednesday, same time, same channel. So we'll have company presentations, student presentations, faculty presentations. Next week, we'll have Ned Burnell speaking about a worker-centered approach to convex optimization in engineering design. And I invite you back. Everybody stay safe and enjoy the rest of your day. And thank you.
Thank you, everyone.
Thanks, everyone.